battery or cell has two connections on its output. The positive and the negative connections, often referred to as its polarity, which is indicated, as you can see with this cell here, with a minus sign and a plus sign. And sometimes you don't have this information provided on the battery or cell to help you quickly decipher its polarity. So you have to take advantage of your digital multimeter to measure voltage while also deciphering the cell polarity. So to do that, let's say your digital multimeter is in its off state. You have to put it on and dial it to voltage reading, which is specified by this uppercase V suffixed with a dash sign and a dotted dash beneath the dash sign, and this is indicative of DC voltage reading. So since our cells comes in DC voltage, now what we do basically is probe the terminal of our cell so we can get its voltage while also figuring out its polarity. The cell is 3.26 volts. If we reverse the reading by switching a probe, now the reading is prefixed with a minus sign, and this minus sign tells us this isn't the appropriate way to measure the voltage of our cell. We should always do the normal reading instead of the reverse reading. So this is it. When you have your cell voltage reading precluding the dash or minus sign, it tells you the black probe from your meter is on the negative pole or connection of the battery, and the red probe is on the positive terminal of your battery or cell. So this is basically how you measure the voltage of a cell or battery while also deciphering its polarity, in case the polarity isn't specified on a cell. This information vis-a-vis our polarity can come pretty handy when wiring cells into batteries, so you don't make expensive mistakes that perhaps damage your cells or battery. In addition to the polarity, you also have information vis-a-vis the cell rating and its voltage, and this cell announces itself as GL 104266P, and its current rating is 3.2 ampere hours or 3200 milliampere hours, and its voltage rating is 3.7 volts. We don't have the energy rating provided, but we can quickly calculate the energy rating for the cell by multiplying its voltage of 3.7 volts by its current of 3.2 ampere hours, and this gives us 11.84 watt hours as the energy rating for this cell. So this is basically how you determine energy rating of a battery or cell from its voltage and current. You multiply current by voltage or voltage by current and vice versa. We have another cell here announcing itself as a cylindrical lithium ion cell. The fact that this is a lithium ion cell tells us it's 3.7 volts, and the manufacturer does a nice job of providing essential details, including the cell nominal voltage of 3.7 volts and peak voltage of 4.2 volts, and also the current is specified 2 ampere hours or 2000 milliampere hours, which if you multiply by the nominal voltage of 3.7 volts, you get 4.7 watts hours as the energy rating for this cell. So this is pretty good. Here is another cell announcing itself as ICR 18650-26J from Samsung, and except for the fact that it doesn't provide additional information to help us identify its type, current, and energy rating, so we don't even know what its voltage is. But what we can do when working with cells like this, for which details aren't specified on its label, we go to a site called Second Life Storage, which provides a large database for lithium cells, and we can run the ID of this cell, which is ICR 18650-26J, on the database, and the database will return information vis-a-vis the rating of this cell, And for the most part, when working with cells, you can often rely on the information you get for second life storage. Suppose you have a new cell. If I obtain a new ICR 18650-26J cell and I want to quickly pull its details, I can go to secondlifestorage.com and I can use the details, or I can apply the details I get from the database to my cell. However, when I'm working with an old cell like this one I have in my hands, I can't apply the information because this cell might have suffered some degradation, and I can rate it as 2.6 ampere hours because I see its current rating on secondary life storage being 2.6 ampere hours. So let's move on to measure cell voltage. A while ago, while deciphering the polarity of our cell here, we measure its voltage. But in this segment, we perhaps look at voltage measuring on 3 different cells briefly, because this can come pretty handy when combining cells. You want to maintain a feature we often refer to as balancing across your entire battery pack. You want to make sure that if you have multiple cells in series, these cells will have the same current and the same voltage. To measure the voltage of your cell or battery, you have your meter dialed to the DC voltage measuring position, which is indicated by the uppercase V suffixed with a dash and a dotted dash beneath the dash. This cell here has its positive pole here and its negative pole here. So we're going to probe this terminal with a black probe from the meter, and the red probe goes on the positive pole. So this is what we're getting. We're getting 3.18, 3.19. So this is the cell's voltage. It's a nominal voltage. This is a LiFePO4 prismatic cell, and LiFePO4 has a nominal voltage of 3.2 volts and a peak voltage of 3.65 volts. For the cylindrical cell, it has the same architecture as this, or the same chemical composition as this, except for the fact that this is a lithium ion polymer cell. But both are lithium ion cells. We can measure this guy's voltage, and we've got 3.84 volts on this one, 3.4 going dangling between 3.4 3.5 volts. This is basically how you measure the voltage of cells and batteries. So now that we can measure voltage of cells and batteries and even decipher a cell polarity, so we can properly wire cells into a battery, we'll move on to wiring cells into batteries. To wire cells into batteries, we make one of 2 connections or both. So we have the parallel and series connection. We have the parallel and the series connections. You make use of either of this, or you make use of both connections depending on your battery design. So we begin with the series connection, and let's say we want to make a 12 volts battery, and each of these cells here is 4 volts. We have to stack up 3 cells in series. Having 3 cells in series will give us 12 volts, and the way we do that is we have cell 1, cell 2, and this is cell 3, and we have the positive, the negative pole, the positive pole, negative, positive, negative, positive. So one of the basic rules for wiring cells in series is connecting negative to positive or positive to negative and vice versa. So when I take the positive of the first cell and hook it up to the negative of the second cell, and I measure voltage across the second cell, I'll have 8 volts. Let's say we have 4 volts here, 8V, and this is 0 volts, or negative or connection. If I place my black probe here and I place my red probe here, I get 4 volts. And if I move across this to the second cell, I'll get 8 volts. And all I have to do to get 8 volts is wire these 2 cells in series by taking the positive of this cell and hooking it up to the negative of this cell. and I can reverse it by hooking the negative to the positive of the other cell, and I can still get my 8 volts battery. So this is C1, and let's say C1 is 4 volts 2 Ah, and C2 is 4 volts 2 Ah. Remember a while ago we talked about the balancing feature of lithium batteries that allows the battery to function efficiently. So you want to make sure across your cell packs, if you have cell pack 1, cell pack 2, you want to make sure that the same current and the same voltage you have here is what you have on the second pack. So you're maintaining balancing for your entire battery pack in order for the battery to function efficiently. And now that we have 2 packs and we can get 8 volts on this side, we can move on to wire the third or last cell pack that we need to make our 12 volts battery. To do that, we take the positive connection from the cell and wire it to the negative connection of the third cell, and we measure voltage across the third cell to get 12 volts. Keep in mind that we've been able to make 12 volts 2 ampere hours battery because the series connection we've done thus far gives us 12 volts while maintaining the current, which is 2 ampere hours. So we have a 12 volts 2 ampere hours battery. By connecting in series, you're increasing voltage, but the current remains the same. You have the voltage from here added to the voltage and added to the voltage on this one, and then you have your 12 volts, but the current isn't adding up. So we have 2 ampere hours. And that brings us to the second example, which is wiring cells in parallel. Let's say we want to increase the current of our 12 volts battery pack. We have a load, perhaps a device to power with this 12 volts battery, and the device, the 12 volts device is rated 2 amps. So what this means basically is that the device will draw 2 amps per hour from the battery, and our battery is 12 volts 2 ampere hours. So 2 ampere hours, pay attention to ampere hours and amps. Amp is the amount of current that a device draws, whereas ampere hours is the amount of current that a battery stores. So our battery has 2 ampere hours. It means that our battery is able to drive the 2 amp load for 1 hour. But we want to notch up the current of our 12 volts battery to 8 amps so that we can drive this 2 amp load for 4 hours. What we do is we start stacking up more cells in parallel. So we have our 4 cell pack here, and we can have 4 cells in this 4 cell pack. Since we want to make 8 amp 12 volts battery, and we've got 2 ampere hours on each of the cells. So what we do, we have minus, plus, minus, plus, minus, and plus, minus, plus. Then to achieve a parallel connection and notch up the current of our first battery pack, we wire the negative connections of all the cells together, and we do the same for the positive poles. We wire all the positive poles, and then we can have if we measure across the 4 cell pack, we still have our 4 volts, but the current is gone up from 2 ampere hours to 8 ampere hours. So on our 4 cell pack, we have 4 volts, 8 ampere hours. And we want to make a 12 volts battery of 8 ampere hours. That being the case, we have to make our second battery pack. Then we hook this up to this. And notice that we're connecting the positive pole of the 4 cell pack to the negative pole of the second cell pack. So this will give us this will give us a 2S battery connection. And this 2S battery connection, if we measure its voltage across the second battery pack, what we get is 8 volts. Then on this side we have 0 volts. Then here we have 4 volts. And this understanding how your battery is wired, or how the various connections is done on a battery, can help you quickly decipher the process of wiring your BMS to your battery. So on some BMSs you see 0 volts, 4 volts, 8 volts, and the last pack will give us our 12 volts. We have our 12 volts, and this entire battery pack will give us 12 volts, 8 ampere hours. So this is basically how you build a 12 volt and 8 ampere hour battery from 2 ampere hour cells, or from cells which are rated each 2 ampere hours. And if you want to make if you want to stack more cells, or perhaps you want to notch up the current of your battery pack, perhaps you can stack up more cells. Maybe you add an additional cell to this pack, and it gives you 10 ampere hours. And you remember, you always have to do the same for all the cell packs, because you want to have the same current across all the cell packs, and you also want to maintain the same voltage. So if you have 4 volts here, you have to have 4 volts here, you have to have 4 volts here. If you have 4.1 volts here, 4.1 volts, it has to be 4.1 volts here. If it's 3.7 here, it has to be 3.7 here, and it has to be 3.7 here. And when you have a battery that is properly balanced, you can guarantee the efficiency of your battery. But when a battery is hooked up to a load, or a load is hooked up to a battery, and the load is taking current from the battery, sometimes you can experience imbalance across the cell pack, like the voltage not being properly balanced. So that's where BMS can come in pretty handy. Your BMS, or battery management system, will ensure that you have the same voltage across the entire battery pack. Okay, let's demonstrate this battery build process in a more practical sense using lithium-ion cells that we've got here. Let's say for the first example of wiring cells in series, we've got 3 cells connected in series. This is our cell pack 1, our battery pack 1, and this is the second pack. This is the second pack, and this is our third or last pack. Now let's take these guys apart. You have cell pack 1 being 4 volts, and cell pack 2 being 4 volts. If you take these guys and you wire them in parallel, what you get is a 2S battery pack, a 2 series battery pack, which gives you 8 volts on this end. So if I probe, okay, if I probe this battery, placing my black probe on the negative of the 4 cell pack, placing the red probe on the positive of the last cell pack, what I get is the voltage for the 2 packs. And as you can see, I'm getting 7.4, 7.5 volts. So this is a sum of the voltage of these 2 cell packs. And if I want to make a 12 volts battery pack, I add an extra pack to the existing 2S series. Now I have 3S, and if I measure voltage across the last cell pack, so I'm getting 11.31, 11.30 volts. So this is the voltage, the 11.31 is the voltage for the 3S pack. And when the pack is fully charged, we get 12 volts. And since each of these cells has a peak voltage of 4.2, when we notch up the voltage for each cell pack to 4.2, we get 12.6. We get 12.6 volts as the peak voltage for our battery, 12.6 volts. And you would wonder, suppose we have a load that is rated 12 volts, 2 amps, and we have a battery pack that is 12.6 volts. How do we manage the extra 0.6 volts? A load has what's known as voltage tolerance. Every device has what is known as voltage tolerance, and the voltage tolerance can be maybe 3 volts, 5 volts, or maybe even 10 volts. I've seen some 12 volts devices that you can hook them up to a 24 volt battery and they will work pretty fine. It's because of this voltage tolerance that a battery of 12 volts is able to handle 12.6 volts, 13 volts, 14 volts, 14.5 volts, as the case would be with live PO cells wired in 4 series. Because for the most part, you always have these guys wired in 4 series. And if you wire 3.65 volts in 4 series, what you get is 14.6, 14.5, 14.6 volts. And a 12 volts device will handle that without complaining at all because of its voltage tolerance.